hopefully I can finish light. And I've talked with the other class. The most important thing for you guys to do is to figure out which part you might not too sure of, and then you gotta go to your notes first, make sure you understand the concepts, and then you come to practice question. And when you practice question, you'll find out like, okay, this part like, I'm struggling with, and then you have to go back to your notes again. Does it make sense? For example, like before when we were talking about 2-point interference pattern, the key thing to understand first, you gotta know what is path difference. If you don't know what path difference is, and then you can't analyze the question, right? So if you feel like, oh, this question I don't know, first you go look at the keywords, say, oh, it talks about path difference, I've got to go understand what path difference is. Like, this is the pattern we are talking about. Does that make sense? And then I'll just quickly show you so that you kind of get an idea of, because your strategy is most important. This is the notes I had, and where you need to understand what's going on. Okay. All right. So now let's quickly have a look of light. All right. So with light, the first one we do is we do reflection of wave. Okay. So if you have a mirror over here, and you have a light coming, and then the rule. What is the rule for reflection? Yeah, incident angle equals to a reflection angle, right? Okay, that angle incident equal to the reflection angle measured by the normal line, right? So this is called the normal line. Okay, and then sometimes they give you a little trick. They will tell you this angle is 50 degrees, and then how big is your incident angle?
40.
Yeah, incident angle equal to reflection angle equal to 40 degrees over here. Okay, so that is something you gotta be careful of. Okay, all right. And then that leads to another one, which is going to be this. If I tell you a wave is traveling to the right, and how do you draw the wavefront? Yeah, the wavefront is always going to be perpendicular to the direction of the wave. So the wavefront, I'll draw it with a different color, is always going to be like that. Obviously, I need to draw the wavelength exactly the same, okay? So you gotta go measure it, okay. So wavefront is always gonna be 90 degrees here. So I just quickly label this as wavefront. Okay, so sometimes you will have question like this. Exactly same question, but instead of asking you to draw the light rays like going like that, they might ask you to draw the wavefront, right? If they ask you to draw the wavefront, well, you'll have to draw it like that. Say that is a wave coming, and then reflect. Okay, need to go that way. 90 degrees to this one, 90 degrees to that one. Okay, my drawing is not the best, but okay, you just need to know, okay, I've got to have 90 degree, 90 degree, 90 degree, 90 degree, 90 degree, 90 degree like that. So all of these 90 degrees will make sure that your wave is going to be reflected properly. Does that make sense? Okay, so this rule is the key to solve the questions kind of like this. Okay, all right, so now the next thing we have is after reflection, we have what we call refraction, right? So refraction is going to, there's two, hold on. I'll draw it on the next page so I have more space. Okay. Okay. With refraction, you need to know whether it's going to be speeding up or not. So first, we're going to understand speed. Okay. So first, understand speed. Let me do it over here. Speed of light. I will use one example, and speed of, let's say, sound. Let's say in speed of light, when is speed of light going to be the biggest? Yeah, so it's going to go faster in vacuum. Bracket, I'll say air. We consider them in vacuum and air, they're traveling at the same speed. And then when it goes into water or glass, it will actually slow down, right? Okay, I'm going to use water as example, okay? Well, why is that? Because light, we call it electromagnetic wave. And these waves, they do not need a medium to travel. In fact, if you have a medium, it will start interacting with the medium, actually slow you down, okay? So where a sound wave is what we call a mechanical wave. Well, a mechanical wave needs a medium to travel. The more medium, the more dense it is, the better for it to travel. Does it make sense? Okay, so and then what it is over here is gonna be, it can't even travel in vacuum, right? Yeah, so it can't even travel in vacuum, so I have to say air, okay? So slow in air, which is gonna be 330 meters per second, and then faster in water. Thousand 500 meters per second. Okay, so yeah, if you don't have time to write down, that's fine, because don't worry about writing it down now, because we're just gonna listen, because it's all gonna be online, okay? All the notes are here as well, okay? So now, when I look at this situation, I need to think, well, is it gonna be slowed down or speed up? Right? So according to what kind of wave it is. Well, let's do our simple one. The simple one we have is the one we always do, which is going to be light wave, right? I'm going to say this is going to be light and air to water. And let's say it's going from water to air. I don't know why the air is down there, but let's just say that's the case. Okay, now we know it's going to be slowing down or speed up, right? Okay, so let's say that's slow down. Okay, slow down. I need to bang towards the normal line, right? Okay, it's something you need to remember. Down that way. Cool. And this one is going to speed up, so it's going to go up like that. Cool. Okay, and why does that happen? There is another diagram we need to understand, which is going to be the wavefront diagram. So it's going to look like this. Okay, and then over here, I'm going to draw some wavefront. The wave is coming like that. And when you have it, is it slowing down or speed up? Slow down, right? If it slow down, does it bend backwards or bend forward? Backward. You need to slow, right? It's slow. Slow is behind. If you're slow, you fall behind, right? So I need to fall behind compared to those ones. Fall behind. Fall behind. Fall behind. Wavelength becomes smaller. Yeah. Okay. So again, I can think about this one with the other one. It should be, I can draw it on here as well. It should be like 90 degrees, right? Like that. And then slow down, the wavelength becomes smaller like that. Does that make sense? Okay. And then same with the bottom situation. The bottom situation is going to be like this. Well, the wavelength is going to come. I'm just doing a rough drawing because I don't have my ruler. I'm drawing on my iPad, okay? All right, so now it's going to speed up. If it speed up, it's going to bend forward or backward. Forward, yeah. If you're fast, you're going to go ahead, right? So you're going to bend forward, going to start to bend this way. Don't bend too much, just bend a little bit as long as you can show. And then the wavelengths become bigger. So the wavelength is going to become bigger. Then now you're going in this direction now. Does it make sense? Okay. And obviously, they ask you the reason why I didn't draw on top of it. You know, I could have drawn it on top of this one as well, like that, and then start bending forward like that, right? With 90 degrees over there. The reason why I didn't draw that is because this question normally they will ask you like separately, and then typically they will talk about the water wave, right? Water going from a deep water to shallow water, or shallow water going to deep water. What happened to the wavefront? So that is exactly the same of this one. Doesn't make sense? Okay.
So that one's deep to shallow.
Okay.
Was that deep to shallow?
If deep to shallow, it's gonna slow down.
Okay.
Okay. So I'll just quickly talk about that one over here. Say this. You think about this. If you go to the beach, do you see big waves close to shore or away from shore? Wave actually breaks at the beach. Okay, wave does not break over there. Say this. So if this is a beach, okay, I'll draw it like this. If this is a beach, right, the water is getting deeper and deeper like that, right? So when the water is close to shore, it actually lifts up. And when the water is away over here, it's actually very, very mellow, okay? So because I like surfing, so if you go into the water, you observe the water, you see, you look at this, you're starting to get excited because you need to get ready, okay? And then when these energy over here, all these energy spread out in the big area, and then they're gonna come close to it here, and then they're gonna lift it up like that. Well, why is that? You look at the wavelengths. There is a big wavelength over here, and there's a small wavelength over here, right? According to the wavelength, then you will know the speed. V equal F lambda. A small wavelength, it means it will have a small speed, right? Okay, so this is good because I don't want to go surfing over here 500 kilometer away from the shore. I want to surf right next to the shore so then I can just go back to the beach. Does it make sense? Yeah, so this is how you can remember the speed of a wave is going to be fast in deep ocean, and it's going to slow down when it comes close to you, and which concentrates the energy, and then the energy can break down. That's why you see all the breaks over here. Cool? Okay, so that is that. Okay, so I want to do one thing, and this is so cool about the iPad. You can do something like this. The question, so the question might be like, maybe like this. Because sometimes they will give you like a sideways like line. That is where the water is going to be meeting the thing. Does it make sense? They might give you an angle like this, right? And you're drawing exactly the same thing. You just need to remember that what I need to do is I need to make sure I just draw parallel lines and joining the dots. So now all of a sudden the wave is coming from this direction and start bending that direction now. Does that make sense? Okay, you just need to make sure when you draw it, you're gonna control the direction and the wave, join the wave, and then think whether it's slowing down or speed up, bend forward or bend backwards. Does it make sense? Okay. Because visually it could be challenging for some students. Like, oh, now the line start become this. What do I do now? Now the wave is coming in this direction. What do I do now? Focus on the concept. The concept is whether it's speed up or slow down, because that's what makes a change. Okay. All right. So let me just quickly give you an example here. So, for example, now the wave is gonna look like this. Okay. And I don't care if it's sound wave or water wave or any wave, or if it's or if it's light wave. I just care about whether it's speeding up or slow down, right? So I need to judge according to my understanding of this part over here. If I understand that, and then I've decided, okay, so now the wave has speed up. So if I know now the wave is speed up, I join the lines. Hey, speed up a little bit, bend forward, speed up a little bit, bend forward, speed up. So now I need to keep the wavelength the same. So now the wavelength has become this side here. Like that. See, V equal F lambda speed up give you bigger wavelength. And then the frequency do not change, right? So that's how I do this kind of question, okay? All right, so moving on to the next part. So next part, we talk about refraction. So now we have an equation that we need to use, which is what we call Snell's law, right? So Snell's law is like this.
Wait, so is this for waves or light?
This is for light.
Okay.
Yeah. This is theta 1, there's an N1 here. This is theta 2, there's an N2 here. So the Snell's law says this. N1 sine theta 1 will always equal to N2 sine theta 2. Right? And you can call whatever is N1, whatever is N2, does not matter as long as they correspond to each other. So N air sine theta air will equal to N water sine theta water, for example. Okay? All right. And then the next part is this. The next part is over here, you might need to have other equations over here. We have something like this. N1 over N2 equal to V2 over V1 equal to lambda 2 over lambda 1. Basically also equal to sine theta 2 over sine theta 1. These two equations will be given to you. And what kind of wave are we dealing with over here? And this is light wave, okay? So the light wave, because we have a refractive index, the more dense, optically dense, not just dense, the more optically dense, the more slow light wave becomes, okay? Okay, I'll say here, the more optically dense, let's say, and use the extreme situation, N diamond is 2.5. The more optically dense, the slower the light. Okay, make sure you add the keyword optically dense, okay? Yeah.
When you're calculating like the refractive index of a total internal reflection, where do you put the 90 degrees?
Okay, yeah, so that's the next part. So when the total internal reflection happen, so is the criteria for total internal reflection. What are the two criteria? First, it has to go light. Yeah, light go from optical dense medium to a light medium. And then second one is light. Second one is incident angle need to be bigger than critical angle. Right? Always test you this. So that is the two criteria. Okay, and now the key thing is, well, what is going to be critical angle? So critical angle, I'll define here. What is critical angle? Critical angle is incident angle when refraction angle becomes 90 degrees. Okay, and then I'll quickly draw a diagram. What does it look like? If it's traveling at the critical angle here, and then the refractive angle becomes 90 degrees. So there's a 90 degree over here. There is a critical angle over here. Cool? Yeah. So normally the critical angle we're talking about coming from a glass to air situation, right? So, well, that means, let me call this N1, this is N2. I have to remember this diagram, okay? I don't force myself to remember other things. N1 sine critical angle will equal to N2 sine 90 degree.
Wait, so in one would
Be glass, dense medium, yeah, dense medium.
another one would be air.
Yeah, all right here, say glass. That's air, okay? Okay, and there is a way of cheating. So there is a cheating equation. If it's air, sine critical angle equal 1 over n. Okay, you can remember this one, make it easier. You don't need to worry about sine theta 90 degrees, because sine 90 degrees is 1, okay? In fact, in Cambridge, this is a Cambridge system. They make you remember this equation instead of using the Snell's law equation. That makes it a lot easier. You just need to remember this equation, okay? But I feel like our equation is more comprehensive, because if this is not air anymore, you might be going from a diamond going to water, because when I'm in water, when I'm diving in water, I also want to appreciate how shiny my diamond is. So then you might have this N1 and N2, you need to use water. But this is only true applying for air situation, okay? Okay, so next one, whichever way you found easy, okay? Okay. And then the next one, dispersion of light, we're talking about refraction. Okay, when a white light is coming, a white light is made out of different lights. This is white. Okay, and then it's gonna reflect. Red is gonna reflect a bit less. And then violet is gonna reflect more. Okay. It's going to be banked more. Okay, so, but don't bend too much, just bend a little bit, because in reality it just changes a little bit, right? Okay, and then violet is going to come down here. Okay. And how do you remember this? Because you look at the rainbow, red is always on top, and violet is always at bottom. Right? That's because light get bended by different amount according to what frequency they have, right? So that was that. And then you remember the order as well. And a little trick again, if it can be a very difficult question, they might ask you, oh, where is ultraviolet light will be? And then you need to know, well, red to violet, ultraviolet is stronger than violet. So if it comes to this situation, UV ray will be even lower, going to be banked. Okay? Infrared is going to be a little bit weaker. So then infrared is going to be higher than red. Okay? So, but hopefully they wouldn't make it that difficult. Okay, so that's that part. Okay, so now I'll just quickly talk about diffraction, because diffraction is an easy one. Just a little thing you need to do. Oh. So you've done this many, many times. If you have a wave coming and the wavelength equal to the thing, so the wavelengths don't change because that depends on the speed. Speed is not changing. If the gap is really big, okay, make sure you use a ruler to measure. This one is only going to bend a little bit. Like that, right? And where this one is going to bend a lot, at all circumstances, I need to keep the wavelength the same. So I need to draw like a perfect circle to make sure the wavelength is the same. Some students draw something like this, true. Or like went down like that. If you went down like that, you look at the wavelength has become a lot smaller than your original wavelength, right? So that's why the curve is going to be a perfect curve that is going to be, you know, use a compass if you want to be real perfect. Something like that, right? Okay, or you just try to be as best as you can, okay? All right. So that is that. And then the next part will be, sometimes you might have this. You have a situation, say you are inside a mountain. Or over here, there's another diagram. The other diagram is if it's a rock. If it's a rock, it's going to bend around the rock, right? It's going to be the same situation. I don't want to draw every situation. I just want to point out what are the things that you need to watch out for, and they should be in your notes. Okay. All right. So another situation where you need to watch out for is this. Say you might be comparing a FM radio to a AM radio, right? Which one have a longer wavelength? AM, yeah, longer wavelength. This is more diffraction. Yes, you do need to know this. Shorter wavelength, less diffraction. If you know this, very easy. If you don't know this, you can still solve the problem. Because the question is going to ask you like this. They say when you are driving inside a mountain, you could hear this radio station 1. Radio station 1. After a while, you can't hear radio station 1 anymore, but now you can hear radio station 2, right? So what's different about 1 and 2? Yeah. So 1, the wavelength is short, so that it didn't diffract, and after a while, it get blocked by the mountain. Does it make sense? And then where 2 have a very long wavelength, so it can diffract around the mountain, so you can still hear it. Does it make sense? Yeah. And this question comes in many, many forms. And another typical form is this. If I hide behind this door, and I want to say, hey, can you guys still see me? Yes, you can hear me. So why can you hear me? Because the sound wave is a lot longer wavelength. It can bend around and diffract around, right? Where light wave is very short, so you can't see it. And right? It comes in many forms. So for example, this year, if I'm the examiner, right, I want to talk about 5G. Because the 5G has very high frequency. If it has very high frequency, it can give you a lot of data, which is really, really good for your speed of internet if you want to download something, high frequency, right? But, yeah, V equal F lambda, if the frequency becomes very high, and light wave, 5G is a light wave. In fact, it's a microwave, okay? That's why some people say you might be cooked. So that's why they need to burn it down. But you wouldn't be cooked. So if speed don't change, 5G has a very small wavelength. If you have a very small wavelength, 5G do not diffract very well. Okay? So what you find out was when I'm here, my 5G is working, and when I went around the corner, now my 5G is not working anymore because it doesn't diffract very well. So that's why 5G, you're gonna have a lot of towers everywhere so that it can bend around the corners and reaching every corner. Does it make sense? So yeah, so that's why, okay? All right, so now, again, the key thing is you're gonna be so familiar with all these different situations, and then when you do a question, you know immediately, oh, this one is about diffraction. Oh, this one is about refraction. Then you're gonna be very, very familiar with that, okay? All right, so now, the last bit is the bit where you guys probably do not enjoy the most, and I do not enjoy teaching this every year as well. That's because, yeah, take a seat. Yeah, that's because every year I have to draw it, and it's super annoying. And let me think if I have a way of cheating. No, I don't have a way of cheating, but I think I have my notes. Okay, I'll just quickly grab my notes.
Is this lenses and mirrors? I don't like this. Is it lenses and mirrors? Mirror is fine. Like the properties.
Okay, so I've got some notes here. Okay, shh. Quickly, does people know how many minutes do we have left for this period? 10 minutes, okay, sweet. Then we'll quickly talk about this. That should be enough time because I have to teach the next period. Okay, so this picture over here, I want to emphasize is this is how a virtual image can be found, okay? Every morning I look in the picture when I do my hair, and this is what happens. So the light coming from my head goes into the image in billions of angles, and they're all gonna be reflected out, right? However, when I retract all of them back, it will meet over this point as if it's coming from this point, right? So in that way, I see a virtual image over here because light rays do not actually come from here, right? And the character about a virtual image is you cannot capture it by a screen. If I put a screen here, I can't capture it because it's actually behind the mirror. Does it make sense? Okay, key thing here is I've got to use solid line here, and I've got to use dotted line over here. Dotted line is not real light. Solid line is real light. Does that make sense? Okay, this is all written here. You guys can have a look of the video later if you want. Real image, what is real image? Light ray actually meets. Virtual image, light ray do not meet. When it's upright, inverted, enlarged, diminished, or same size. Those are the key words we've all agreed to use to describe the image. Does it make sense? So you need to remember those keywords.
Just memorize like what?
Yeah. Okay.
So long.
Yeah.
Well, while you put the video,
Oh, I will put it on YouTube and then either send it to your emails or put on Google Classroom. Yeah, okay. All right, so, sure. Okay, and then we have concave, convex mirror. I will talk about mirror. Lens are exactly the same situation. You remember the rule. The rule is if it's parallel, it goes through focal. If it's focal, it goes through parallel, become parallel, right? And that is the rule. And then you need to remember which one is concave. Concave one have a cave, right? Convex one, oh, this is a cave. Oh, this is both cave. Oh, this is all caves. So this is a convex one, right? So if it's a lens, well, this is convex, and this is cave. Look, there's a cave, right? So concave. Okay, and then whether it's converging light or diverging light, you need to go draw it. So what my past experience is it doesn't matter how many times I draw it with the student have to draw it themselves and make mistakes. Then they look at it, they'll be like, okay, that is a mistake. Then I need to change it. Because there's just too many of them, they can be confused, right? Okay, so now, here I point out, this is called center of curvature. What is center of curvature? This mirror is a big circle, a big round circle. And this is the center, and this is a radius, r, okay? And your focal point is half the distance of r. So the question might tell you, say the radius is gonna be 50 centimeter, that means the center of the focal length is 25, okay? All right, and when we use the equation, so I'll quickly mention the equation here as well. So the equation we have is 1 over f equal 1 over di plus 1 over do, right? I mean, that's all easy. You just put the number in and then you just do the math, right? So using your calculator. So the key thing over here is this di could be positive or it could be negative. And then this focal length, it could be positive or negative, right? And what is the rule? The rule, if it's virtual, if it's real, it's positive. If it's virtual, it's gonna be negative. Does it make sense? Okay, so now, for example, if the question tells you this is gonna be a dentist mirror, okay? And think about dentist mirror. You guys all go see dentist. The dentist mirror is put inside your teeth and for you to have a look that if the teeth is going to be good or not, right? It won't enlarge. Is it going to be a real image or virtual image? Virtual, because they can't form an image inside your mouth, right? So, and they just want to look how big it is, okay? So that is a virtual image. So when I calculate it, if they give me di, I need to know I must use negative for that di. Does it make sense? Okay, and then, well, what about if? Is if going to be positive or negative? Then you have to think, what kind of mirror is dentist mirror? And dentist mirror is going to be a concave mirror, okay? In fact, I think I have it over here. Here. The dentist mirror is going to be this situation. You put the object really close to the mirror, which is the teeth, and then the light ray has been converged, but it's still diverging out. Okay, and then it never meets, so it will look like it comes from over here, forming a really big image. Okay, in that case, you know this is a virtual image, but it is actually a real focal point. Okay, so coming back here, this is a real focal point for this lens. So I know here must be a positive value for this one. Okay, yep.
Can you explain when it's like converging and diverging?
Okay, so what does converging, diverging mean? The word converging just means coming together. As a class, we're converging because we have come together. Some students have diverged out, went home or went to shopping malls. So that is diverge. So you just look at the light ray, whether they're pointing together or pointing out. Okay? So for example, I look at this one. If I tell you this mirror, is it converging, diverging? I have to look at this picture. Honestly, I don't even remember. if you ask me, say, convex mirror, is it converging, diverging? What do? I will think first, convex mirror, I'll change it to Chinese, or maybe sometimes I don't. Okay, convex mirror, it doesn't have a cave. I remember it doesn't have a cave. And then I need to remember, okay, so it will have this shape. That doesn't have a cave. And then I think, oh, that is a mirror. It's not a lens. So it's going to be something like this, right? And then if you ask me, say, oh, is it converging or diverging? Okay, I need to think. Let me imagine all these light rays coming. What's going to happen to them? And I have a look. Oh, yeah, all of the experiments I've done, these are going to go out like that. Then you say, oh, is this converging, diverging? Diverging. They're moving away. Does it make sense?
Yeah.
Okay, if you make up another one, you say, oh, concave mirror. Or concave lens, right? Concave lens. Okay, let's think. Concave. This is cave, and this is the lens, right? What's happening? Is it converging or diverging? I remember the picture. Oh, yeah, it's diverging out, right? And that's diverge. Is it real focal point or virtual focal point? It's not going to meet over here. That's going to be a virtual focal point. So that is going to be a virtual focal point. And so then, am I using positive or using negative? Hey, I need to use negative. I go over there. Does that make sense? Okay, before you go, can I just say something? Okay, I'm going to flip this. You can stop. What you need to do is you need to be able to draw 1, 2, 3, 4, 5, 6. 6 for mirror, 6 for lenses. And then you also need to remember the application. Dentist mirror, magnifying glass, which one it is, and then all of that. You just do it. It's not very hard. Once you remember it, you go anywhere. Yeah, and that's it. That's all. I'll put both of them up.